Well, good afternoon. It's 2:40. I'm 10 minutes late getting started, but mostly because next door a class was in the other class's room, so I was having to try to work that out. Plus, I had a student in the earlier section needed a test copied and to pick up some other tests, so I had to go down to the office and do that. So, running a little late today. Today has been one crazy day all day long. And right now I have no students in this class, so the craziness kind of continues. But I won't go into all the details of how crazy it's been, but just nothing has worked as it's supposed to today so far, first time through, or very little has. So let's get started with today. I'll hold off and give you the announcements if and when anyone actually comes in. Right now I'm the only one in the class. This is differential equations, Math 238. So, picking up from there, all right. Where we left off last time was in Chapter 2, First Order Differential Equations, 2.6, a numerical method. And I think we were down to the point of where we say the caveat on page 79. Euler's method is just one of many different ways in which a solution of a differential equation can be approximated. Although attractive for its simplicity, Euler's method is seldom used in serious calculations. So introduced here just to give you a first taste in numerical methods. We'll go into greater detail in discussing numerical methods that give significantly greater accuracy, notably the fourth order Runge-Kutta, I think is how you pronounce that, or often referred to as RK4 method. That's in Chapter 9. Okay. Now, that's another somewhat analytical model. Okay. And they do give you on the figure on page 80 of how Runge-Kutta 4 guarantees 4 points, well, actually 5 they show here, of exactness, okay, whereas Euler's method constantly is getting further and further off, okay. Now, the later part, going back to page 79, numerical solvers. They're actually I would say, I don't know this for a fact, but I would say that probably more and more things are going to numerical solvers than even something like fourth order Runge-Kutta method, which is greater accuracy than Euler, but still not exactly probably where you want it. And basically these are doing computer programs, or maybe getting some pre-canned computer programs that'll do this for you. That some of these are called finite difference problems, and some of them are called finite, goodness, I can't remember the two names. They're somewhat similar, but it actually is doing sort of an iterative approach that you basically set up your differential equation just as you read it, and you have anytime you have a dx or a dy, that actually is a delta x or delta y, and you're working through that. You let your x get smaller and smaller and smaller and calculate your y, and when you get within a certain accuracy, you say that's close enough, we'll stop. And I don't see the specifics listed here, but they do talk about numerical solvers. And they sometimes, though, they give an illustration here, a not very helpful numerical solver solution curve. In every one of these approximation techniques, you're going to have some sort of issue. and they show a not very helpful numerical solution curve for a problem that should be a pretty simple problem. And they talk about it some. That's using a numerical solver. Since we don't have them, we're not going to do them. So I just wanted to at least introduce them to you. I think you've probably already given you these, but homework exercises in 2.6. Do number 1, it should be in the back. Number 3 should be in the back. Any of the odds 5 through 9 that are in the back, do those. 11, you could do that one, and then don't worry with the discussion problem. Okay? So if you need more to work on, the odd number Chapter 2 and review problems are also in the back, so you could do any of the odds 1 through 11. You could do number 13. You could do number 15 and or 17. Any of the odds 19 to 25 that are in the back of the book. Now, all of these will be in the back of the book, I don't think. Probably all the ones I've said so far. But any that are in the back of the book, those are the ones I would choose to do. Any of the odds that are in the back, either 27 or 29, 31 if it's back there, 33 if it's back there, 35 and or 37 if they're back there, and you could try doing Euler's method You could play around with 39 if you'd like. That's up to you completely. Okay. We're not doing the modeling. And I think I gave you the test last time, so if you weren't here last time, you need to get the test from me. But we're not doing the modeling in Chapter 3. Though there's some interesting things to look at. There's a guy named Willard Libby who did carbon dating, which uses differential equations. You can take a look at any of this. Again, it's the sort of modeling situations, and we're, like I said, we're not doing these, so let's move on through that. Chapter 3, I was just sort of paging through it to see if there's any additional stuff that you needed here. But then we go to Chapter 4, higher order differential equations. Okay, this is a very long chapter, so we'll probably spend most of the rest of the term in Chapter 4. Okay, and anything that we have left over, we'll try to move on from there, but I have a feeling we'll be here now. Let me make this one exception here. 4.4 and 4.5 duplicate each other. One's called the superposition approach, the other called the annihilator approach. I've taught it using both ways, and both of them are out there on the YouTube videos. I think I've decided that it seems like students catch on to the undetermined coefficients superposition approach better than annihilator. So we'll probably only do 4.4, but 4.5 will be out there if you need it. Okay? So let's get started in 4.1 then. This is on page 119. Chapter 4, higher order differential equations. And 4.1 is the preliminary theory linear equations. Okay? Now, here's just a few things to review. In Chapter 2, we are able to solve a few first-order differential equations by recognizing them as separable, linear, exact, or having homogeneous coefficients. Okay? Even though the solutions obtained were the form of one parameter family, this family, with one exception, did not represent the general solution of the differential equation. Recall that a general solution is a family of solutions defined on some interval I that contains all the solutions of the differential equations defined on I. Only in the case of linear first-order differential equations were we able to obtain general solutions by paying close attention to certain continuity conditions imposed by the coefficients in the equation. In this chapter, our primary goal is to find general solutions, so that's where we're going to start now. So let's look at 4.1.1, initial value and boundary value problems. We've been doing mostly initial value problems over there. I think every now and then I've mentioned the situation with the boundary value problem. Okay? So let's do a little review on what we mean by linear differential equation. This is going to be nth order because we're doing higher order differential equations in this chapter, initial value problem. Okay, so here's what the generic form of your differential equation will look like. Thank goodness they won't really look like this for sure. They'll be a bit more precise, but we're using generic type phraseology here. So you have, let me get my pen set up. All right. What the A's are standing for here are not numbers, but functions. So this A sub n is a function of x and x alone, no y involved with it, and d nth y dx to the n. Okay? So we're doing higher order differential equations. They're going to have the nth derivative of y, and that's what that stands for. The a sub n is the polynomial function that goes with that nth derivative. The n subscript for a just identifying this is the coefficient function that goes with the nth derivative. Okay? This n really isn't contributing anything except the identifier that identifies this function of x, okay, coefficient function of x with the nth derivative of y, okay, plus a sub n minus 1, and I guess this is just a coefficient function. This is a function of x that goes with the n minus first derivative of y with respect to x to the n minus first, plus a sub n minus 2 of x that goes with d n minus 2, the n minus second derivative of y with respect to x to the n minus second times, okay, plus, and here we'll put our famous little dots, okay, and then we'll pick up at the lower end of the order with a sub 2 d2y dx squared. And this is what all those look like. Oh, I forgot. a2 of x. It's a function of x. Okay, a2 of x times d2y d. So that's what each of these look like. Pick a number, any number. 15. A sub 15 of x, the 15th derivative of y with respect to x to the 15th times. You know, that's what we mean. Okay? The next one, of course, then be plus a sub 1 of x, again a function of x, dy dx, that's the first derivative, plus a sub 0 of x, okay, times y, okay, and that's equal to some g of x, okay. Now all the a's are functions of x alone, all the g's, the g is function of x alone. The y and its derivatives may have x's in them, okay, those are functions of x's as well, but that's the only place that y shows up is in the derivatives or in the function itself, okay. Now, this is a linear function, which means none of these derivatives are raised to any power, or y is not raised to any power. Nor are the derivatives multiplied by each other in any way, like a third derivative multiplied by the first derivative, or a y multiplied by the fifth derivative. Can't have that. You know, each of the, you might say, y terms, whether it's y or derivatives of y, they're functions of various functions of x's, but they're not related to any of the other y's by multiplication, division, or any other way like that. Okay, that's what makes it linear. All right, now, that's your differential equation. Again, this is going to be an initial value problem, IVP. So it's going to be subject to these constraints, you might say. That y of x0 is equal to some y0. Okay? Pick any value of x that you happen to know, and the y at that x0, we're just going to name y0. Give them the same subscript. Let you know they sort of go together as an ordered pair. But you need more than that. You need one of these for every order of differential that you have, save the last one. Okay, so this is the one for the constant term, y prime of x0, and we do the same value of x, and that's equal to y1. Just want to make sure I name it the same thing they do. Y double prime at x0 is going to be y2, just to give you an idea. Okay, and we'll dot this along the way until we get down to our y of the n minus third derivative is equal to y I've got to get my counter right here. Y sub n minus 3. Yeah, it counts the same number as the subscripts, okay, as the derivatives, okay. And then y n minus 2, the nth minus second derivative of y would equal n times y sub n minus 2, and then y sub n minus, the n minus first derivative of y. I've been leaving out, sorry, at x0, at x0, at x0. This is equal to y sub n minus 1. Okay. Now, notice what we have here. Number one, the function y for your initial value problem and all of its derivatives up to the n minus first derivative are all evaluated at the same point, x sub 0. That doesn't have to be the initial value that you had the thing. It doesn't have to be, say, x equals 0 or 1 or anything else like this. It's just at the same point. You know the function is first derivative, second derivative, all the derivatives up to the n minus first derivative. Okay? Now that gives you, if you look at it this way, n ordered pair of values, you might say. Okay, for x0, y0, that is a point, but then the other is y prime at x0 gives you y1, y double prime at x0 gives you y2, y triple prime x0 gives you y3, all the way up to y to the n minus first derivative at x0 would give you y to the n minus 1. Because notice they didn't start counting the I was trying to think of, okay, let me phrase it a different way. You have an nth order differential equation. You have n initial value conditions. They don't go to the n minus first, to the nth derivative. You don't have one there, but you have one at x, at y as y of y0, which is sort of like your 0th derivative of y. It's just y. And then the second one is y first, and then y second, and then y third. And that was the second, third, and fourth boundary conditions, but they're only those derivatives. So the n minus first derivative at x0, and knowing its value y sub n minus 1, that gives you the same, that's your nth boundary condition, initial value condition. Okay, so you do have n of them, but your superscripts, your derivatives don't go to n, they go to only to n minus 1, because your first one was actually the 0th derivative, which is the function itself. I hope that's not too confusing. Okay, recall that for a problem such as this one, we seek a function defined on some interval I that has to contain that x sub 0, of course. Otherwise, all bets are off here. Okay, we've already seen that in case of second order initial value problem, a solution curve must pass through the point x0, y0 and have a slope of y1 at that point. And that basically gives you the first two conditions, because first order differential equation has both of those, covers both of those values. Okay. Now, they do another little blurb here on existence and uniqueness. Okay. All right. Back in section 1.2, we stated a theorem that gave conditions under which existence and uniqueness of a solution of a first-order differential equation were guaranteed. The following theorem gives sufficient conditions for the existence of a unique solution of problem 1. I'm sorry, my throat's going on me. I was going to wait and say this, but let me just take a little break now and go over what part of the day's been like. I'm going to go back to last Friday. We purchased the vehicle I drive up in Jasper. That's where we had a deal with our insurance company. They had a deal with that dealership. We picked the car we wanted. It's called the auto buying thing, and they said they had it, so we went up there and picked it up. So we wound up getting the car in Jasper. So that's where we've been taking it back for service. So I took it for service Friday afternoon. They took care of it, but they came out and said, you have a roofing nail in your right rear tire. We need to fix that, because I had my light come on sometime earlier, but I never could tell which tire had any issue. And I thought it might be the spare if that was also on it. That happened in my last vehicle. I kept trying to figure out what's wrong with the tires, and nothing was, because the spare was low in air. So anyway, I thought, well, maybe that's it here, because it was driving fine, no issue. And they said, nope, that's why the light came on. You lost a little bit of pressure back there, but it kind of sealed itself up. So they said, yeah. I said, yeah, go on and fix it. So they did. That was Friday afternoon. This morning, that tire was flat. Of course, I didn't notice it until I was driving into work. I was a few blocks from home. I said, something doesn't sound right. It doesn't feel right. So I pulled into the parking lot of a business just off the street. Nobody was there, it looked like, and looked, and sure enough, I had a flat tire. So I wanted to call and document this with the dealer that supposedly fixed the tire. It was the same tire. And so I called them. Well, they couldn't do anything. If you bring it by here, we'll take care of it. I said, look, I'm in Birmingham with a flat tire. You're in Jasper. I can't bring it by there. Okay. Oh, yeah, that's right. You could. I said, will your roadside service take care of it? Well, no, they only do engine parts. So that was out of the picture. But they may do it. You give them a call. So I called them and had to do a bunch of the stuff through the phone, you know, texting back and forth and giving them all the information, the VIN and what was wrong and descriptions of it, why, all of this kind of stuff. So after that, I'm not a very fast texter at all. And sometimes it was sending and sometimes it wasn't. So ultimately, I got everything done. And then finally, I called my wife to tell her I was stuck, and then they called back. So I was talking with them, and they said no, they couldn't do anything because they only covered things. But maybe if I could get the dealership to promise them to bill them, the dealership, then they would come out and take care of me. And I said, well, I'm not sure I can talk them into that. How long will it take? Well, it'll take us an hour to get there. Well, I can change a tire in less than an hour. Of course, this was a almost new vehicle, 20,000 mile, you know, and so there wasn't anything real obvious. I mean, I'd not changed the tire on this one before, so I wasn't absolutely certain where everything was, but I figured I could find it. So I proceeded to do that, and then found out there was one lug nut on this tire and on every tire that wouldn't work with the lug wrench. I said, what is going on here? They said, oh, that's and they had a name for it, and said, you have to find the adapter for it. I said, well, there's nothing in the manual. Oh, this is a special feature. Well, they had told me a special feature. They didn't tell me it was a special feature and didn't tell me anything about it, and I probably paid for a special feature I didn't want. So anyway, they told me to look around for a little pouch. I finally found it in the glove box, and it contained a thing that would take off the special lug nut. So it wasn't very handy or easy to do, but it would take them. So I did that, and then got everything, you know, found the jack point. Just everything took a long time. And so finally, bottom line, I was an hour and a half late getting to work, and there went an hour and a half of my 2 hours, office hours in the morning. So I got almost nothing done I had planned to do this morning. And then everything since then, it's just been crazy days all along. You know, the whole day has been nuts. Okay, so anyway, enough of that. Let's move on. So here was the uniqueness of existence of a unique solution. This is theorem 4.1.1. So let me erase this so I can get it on here. Let a sub n, these are things we just saw, a sub n of x, a sub n minus 1 of x, a sub n minus 2 of x, dot, 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 all the way down to, where did we do before, a sub 2 of x, a sub 1 of x, and a sub 0 of x. And I think even throw in there the g of x. Okay. Those, all the a's are the coefficient functions of your derivatives, or the a sub 0 of the function itself, the coefficient function of the function itself, y. And g of x is on the right-hand side. That's what they're all equal to. The combination is equal to. All these are continuous on some interval I. Okay, some interval I. Now, we also have to stipulate a sub n of x cannot be the zero function. Okay, because if it were, if I could go back to my previous slide, which I can't because I just erased it, but if we could go back to there, if the a sub n of x was 0, then you wouldn't have an nth order differential equation. It would be an n minus first order differential equation. So that's the only one of these that you can't have equal to 0. Okay? And this is for every x in the interval. In the interval I. And if x equal x0 as your initial point. It doesn't have to be the first point, but it's any point in the interval. Any point in the interval I, then a solution y of x of the initial value problem that I just had out there before, exists on the interval and is unique. Okay, so what it's saying is, if all these functions are differentiable, not differentiable, continuous on this interval I, and a sub n of x is not equal to 0. Any of the rest of them could be 0, given problems, whatever, but a sub n of x can't be. For every x in I, and if x is equal to x0 on the interval I, then the solution y as a function of x of this interval intermediate initial value problem exists on I and is unique. Okay, so let's look at a few examples. I think I'll erase this so I'll have more room to write here. Okay. We're 3/4 of an hour into the class and still nobody here. So here's an initial value problem. 3y triple prime plus 5y double prime minus y prime plus 7y equals 0. With these conditions, y of 1 is equal to 0, y prime of 1 is equal to 0, and y double prime of 1 is equal to 0. Okay? Now, this is an unusual problem, okay? And here's what's unusual about it, okay? First place, let's just look at the differential equation part of it, okay? Everything on the left-hand side is equal, the sum of all those terms, sum and difference of all those terms is equal to 0. That's on the right-hand side, okay? Now, we know for that to be true, there is at least one solution that's got to be there. It's called the trivial solution. Y and all of its derivatives are equal to 0. Because certainly if y is equal to 0, the first derivative of y is equal to 0, the second derivative of y is equal to 0, the third derivative of y is equal to 0. So if y and all of its derivatives are equal to 0, certainly that is a solution for the problem. Now the other thing that's a little unusual about this, notice that what's in the parentheses, y of x0 and y prime of x0 and y double prime of x0, and remember we go up to n minus 1, okay? Your differential equation goes up to y is equal to 3, but your boundary value only goes up to the second derivative. Okay, there are 3 initial values, but one is the the 0th derivative of y, first derivative of y, and second derivative of y, even though the function differential equation starts with the third derivative. You don't specify the third derivative. Now, what's in the parentheses there, y of 1, y prime of 1, and y double prime of 1, that has to be the same in all 3 initial values. All right. That's what's in parentheses has to be the same in each of it. That's why we call it initial value problem, even though it may not be the first value. 0 may be the first value, but the value at which all these things are defined has to be the same x. What's unusual in this problem is that the value of it, y at 1, y prime of 1, and y double prime of 1, is each also equal to 0, which means that, and by the way, now your condition of theorem 4.1.1 is satisfied. Our coefficients here are not functions of x, they're just coefficients. They're all numerical numbers, 3, 5, -1, and 7, all good numbers, okay? So, and we'll just say they're defined on any interval that contains, well, they're constant functions, so therefore they're continuous functions, okay, on whatever interval you want to choose, okay. And x equal 1 is on that interval, okay, in the interval. Then this is this differential equation, there is a solution that satisfies it and is unique. Well, guess what? We've already identified it. Y is equal to 0. What that tells you then, it is not only a solution, it is the solution, the only solution. Because the theorem says it's there is an initial value problem. If it has a solution, and it does, that first, the solution exists, and secondly, it's a unique solution. So we know the solution exists, and then we know a solution that exists, and because we know a solution, and the solution has to be unique, that is the one and only. Okay. So y is equal to 0 is the only one. So much for nothing. Okay. Now, here is another one. I think I'll go on and erase this because this could take a little more room. They first start with giving the solution. Y is equal to 3e to the 2x. It sort of drives me nuts here. Plus e to the minus 2x minus 3x. They tell you that is a solution to this initial value problem. And here's the initial value problem. Y double prime, let me get a little closer here because I may run out of room. Yuck, it didn't pick. Okay. Whew. Goodness. A little time out here. In addition to everything else that happened today, I had a student from my first class needing some stuff from his from my second class, needing some stuff, well, okay, start over. In my first class, a few people did, have stuff to turn in and stuff, so I was a little late getting down to my office, got out my lunch, and I only had less than 45 minutes to eat, and basically had not quite taken my first bite when there was a knock on the door, and another instructor came in. He was an automotive instructor saying, hey, we need some help on our schedule for summer. So he had to explain the whole thing to me, and then ultimately figured out what we could do and got all that done. And by the time he left, I had probably less than 15 minutes left of my lunch 45 minutes. So I got maybe half my salad eaten, and that's all. So I am running, and then in between classes I was hoping to do it, and that's when the student from my second class needed some copies, because he's also in 2 other classes, including this one, needed some copies of his tests from his other classes. So I had to make copies for one, I found copy for another, and so I got 0 time to eat any lunch. So I'm going today on, since breakfast I've had half a salad, and it was a small salad, so only half of it. So I'm a little loopy as far as thinking goes and writing, so I almost feel dizzy. So here is what they claim is the solution. We need to verify it to this initial value problem. And here is the initial value problem. Y double prime minus 4y is equal to 12x. That's the differential part. The initial conditions are y of 0 is equal to 4, y prime of 0 is equal to 1. Okay, now, just pointing out what we were saying before. Second order partial differential equation is higher order, but not much higher, okay, second. So therefore you need 2 boundary conditions. The function at the initial value, not boundary, initial conditions. The function at the initial condition and just the first derivative of the initial condition. You never need the maximum derivative, second derivative. That can't be a boundary issue, otherwise that's your solution for the problem, okay? So you need the function and its first derivative as the initial conditions. But that's 2 conditions for a second order differential equation, okay? So we need to verify it. Well, how do we verify it? Well, we need to know the second derivative. We can't get that without the first derivative. So let's first take the first derivative. Y prime is equal to 6e to the 2x is 3e to the 2x times derivative of 2x, which is 2, which is 6e to the 2x. Man. Minus e to the minus 2x minus 3. Okay? That's your initial condition. Hang on to that. Now your second derivative is, yuck, my pen drags sometime, especially when I'm tired and I don't hold it far enough off the screen. Be 12 e to the 2x, okay, 6e to the 2x times 2, so it's 12e to the 2x, plus 2e to the 2x, goodness, that's ugly. That's a minus 2. This is being so picky. I'm going to try to erase it and get it to, erase too much. The minus 3 was from up there, plus 2e to the minus 2x. And then the derivative of 3 minus 3 is 0. Okay. Tell you, I may have to pause and go get me something to drink because I'm just rapidly running out of steam. So there is your second derivative. So let's plug that in here. For your y double prime is 12e to the 2x minus 2 or plus 2e to the minus 2x. Goodness gracious, my screen is falling on me, and that contributes to the ugly writing. Okay, minus 4 times your y, which is 3e to the 2x plus e to the minus 2x minus 3x, and that all is equal to 12x. That's the question. Is it? I'm going to try to finish this problem, then try to get something to drink. Okay, let's do it. Clear the parentheses. 12e to the 2x plus 2e to the minus 2x minus 4, well, let's distribute. Man. That's minus 12e to the 2x minus 4 e to the 2x. Yeah, I left off a 2 here, and that made that a plus 4. Okay. Sorry about that. I hope someone caught that earlier. So this is, let me correct all these. All right. All right, I think I've got it now. Goodness gracious. Minus 4e to the 2x plus 12x equal 12x. Well, looky here. 12e to the 2x minus 12e to the 2x plus 4e to the minus 2x. I left off my minus sign there. Minus 4e to the minus 2x. And you got 12x equal 12x. Sure enough, that's true. Okay. You should verify that is a solution. Now that differential equation is linear. Coefficients as well as the g of x equal 12x are continuous. And the, a2x is 1, not 0. So that's fine. On any interval containing x equals 0, we conclude that from the theorem that they feel that the given equation, a given function, is a unique solution on your interval I, any interval that contains 0. All right, I'm going to stop at the red dot there and pause this because I've got to go get something to drink. I don't think I can. Okay, I'm sorry. I'm back now. I'm not sure I'm much better, but I got a little caffeine, a little sugar, drank a soda, or a few sips of a soda. So hopefully I'll make it through the last 10, 15 minutes here that we have. All right, so we've verified that. The requirements of theorem 4.1.1, the uniqueness, type thing, is that all the a sub i's of x's be continuous, and that the first one, a sub n of x, not be 0 for every x, are both important. Specifically, of course, like I already said, if the a sub n of x is equal to 0 for some x in the interval, then the solution to the linear initial value problem may not be unique or even exist because it's not a nth order differential equation then at that value. Okay? So here's an example of that. I think I'll take this off so we can have more room in case we need it to write. Okay? It said you should verify, here's another one. Y is equal to cx squared plus x plus 3 is a solution for the initial value problem. The initial value problem, I've lost it now, x squared y double prime, yep, there it is, minus 2xy prime plus 2y equals 6 for these initial conditions. Y of 0 is equal to 3 and y prime of 0 is equal to 1. Okay. 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 It says on the interval, and this interval is minus infinity to infinity. Okay. Now, for any choice of the parameter C, for any C, that parameter C, in other words, there's no unique solution for the problem. Oh, wait. Okay, we need to verify it first. That's what we're wanting to do. So let's plug and chug and see what we get. Well, we need to do a y prime is equal to 2cx plus 1. Y double prime is equal to 2c. Okay? So let's plug in and see what we get. X squared, 2cx squared, minus 2, let's make that a 4, 2x times 2cx, 4cx squared, minus 2x plus 2 times y, that would be plus 2cx squared plus 2x plus 3. Okay? No, plus 6. Okay, 2 times 3. Okay? And is that equal to 6? Okay? Well, let's see. 2cx squared plus 2cx squared is 4cx squared minus 4cx squared is 0. Minus 2x plus 2x is 0. And 6 equals 6. Yes, that's true. But guess what? It's true for any c you happen to choose. C equals 0, C equals 1, C equals 3,585,000, C equals 4/3 pi. It doesn't matter what C is, it's going to be true no matter what the value of C is. So guess what? That's not a unique solution. And why is it not a unique solution? Because in this interval, right dab in the middle of it, x could equal to 0. But if x equals 0, then your initial condition, your required value is missing. Your a sub n of x, a2x, is 0. And it can't be 0. So therefore, you can't guarantee that that would work. It won't work. Okay? It won't be a unique solution. Now, that was initial value problems. We don't have much time, but let me at least introduce you to the concept of boundary value problems. Another type of problem consists of solving a linear differential equation of order 2 or greater in which the dependent variable y or its derivatives are specified at different points, not at the same point. An initial value problem, even though it doesn't have to be the initial value it has to be some value, constant value problem, I like to call them sometimes, that at the same point you have your function and all your derivatives up to n minus 1 defined at that value. Okay? Now, a boundary value problem, the function y and its derivatives are specified at different points, not at the same one. So here is a sample of one. a2 as a function of x, this is generic form now, d2y dx squared plus a sub 1 as a function of x, dy dx plus a sub 0 as a function of x, y is equal to some g of x. Okay, same as we had before, second order though, only here. And here's your constraints. Subject to y of a is equal to some value y0, and y at some different point b is equal to some y1, some other value, presumably. That's a boundary value problem. You have a value at A and a value at B that sets the bounds. Okay? The prescribed values, y of A equal y0 and y of B equal y1, are called the boundary conditions, or the BCs rather than IVP, initial value. Okay? And this is boundary value problem, BVP. Okay? A solution of the foregoing problem is a function satisfying a differential equation on some interval I that has to contain A and B, and whose graph passes through the 2 points A, y0, and B, y1. Okay? For a second order differential equation, other pairs of boundary conditions could be, and we'll get into that in a second. But first, the values there. I wish, I don't want to, I can't draw the entire graph here, but I'll try to give a good rendition. If people were in the room, I'll just hold it up in the light and let you see it on the board. Of course, that wouldn't help people at home. Sorry, let me not do that. Okay, there's your axes, the y-axis and the x-axis. And you have some interval where these functions are defined. Okay, that's your interval I. Okay. Now, you have a variety of curves. Something like this, something like this, something like this, something like that. All these different curves that could be going up, down, moving all around. But you know that at x equal a, the function has to be some value y0, and at x equal b, it has to be some other value y1. Okay? Got them a little too close to each other. So anyway, these two potential solutions meet those boundary conditions. Okay? Now, either one of those curves will work. You got two boundary conditions, but either solution will work. You may have others that may work as well because they meet those conditions. So they're not as specific or limiting as your initial value problems. day or the other. Now, what are some of the other options you could have? You could have that y prime at A is equal to y0, and y of B could equal y1, or that y of A is equal to y0, and y prime of B could equal to y1, okay? Or that y prime of A is equal to y0, and y prime of B is equal to y0, okay? You could have any one of those sets, okay? And that would be a boundary value problem. One is defined at one value A, the other defined at some other x value B. And it could be both of them could be function values, one a first derivative, one a function, the other is first derivative, or both of them first derivative. Can't do a second one because that's the maximum derivative of your equation, and you only need two boundary values, so you do them like that. Okay. And y0 and y1 are some arbitrary constants. Whatever they happen to be, they are for both cases. Now, as if that wasn't, not that it's all that confusing, but why would you say that enough? Okay. Here is another way to look at it. These three pairs of conditions are just the special cases of the general boundary conditions that would go something like this. Alpha sub 1 y of A plus beta sub 1 y prime A. Okay. I think we're basically out of time. And this is equal to some gamma 1, and then the other was alpha 2 y of A plus beta 2 y prime A. And this is equal to some gamma 2. Okay. Oh man, those are B's there. Okay. And it says here, the next example shows, as the earlier one did, that the boundary value problem may have several solutions, okay, as the figure showed, a unique solution, or no solution at all, okay? And we will begin next time with example 3. I think we're out of time now. Sorry I got started late and then had to take a break in the middle. Not in the middle, toward the end. But I was just absolutely running out of juice before. Just realized, since breakfast this morning, I left home, only drove a mile. I don't even know if it was a full mile or two maybe. And then had to have all the adrenaline rush of having a flat tire and having to deal with the dealership and dealing with the roadside assistance and dealing with everybody there, and then having to physically change the tire, jacking up the car and finding, dealing with the dealership again, and doing all the stuff that was required in changing a tire, loosening the lugs, and doing everything else, getting the tire in and out of the trunk, out and into the truck, all the various things with that. It was quite a bit of expenditure of effort. Though it was effort. that bad, but just something to be doing almost constantly. And then with everything that's happened since then, to have no lunch at all, I mean, half a salad was all, I mean, I am literally out of it. So sorry if it's been a little disjointed today. Evidently, all the students were out of it too, because none of them showed up. So anyway, we'll look forward to seeing you on Wednesday.